Okay, let's start with the last lecture of Francesco.
Yes. Can you hear me? Yes. So first of all, I would like to answer one of the questions from yesterday. So there was this point about this integrating out. So I thought that maybe it's I can spend a couple of minutes explaining how that works out. So the point was that so we were using this gauging technique to start from one duality, and then we have background fields, and we promote one of them to a dynamical field, and we have a sort of Lagrange, one of these dynamical fields appear as a Lagrange multiplier. So we had an action, a Lagrangian of the following form. If you want this, I should write it as a small letter. This was dynamical, and say this is the background. So the question was how this works. And so in particular, the question is if I have a partition function of B, which is a background, so this is a path integral of this type, how do we integrate out this gauge field A? And if you want, the point is here that A is not just one form, it's a gauge field. Okay, so we should treat it as a gauge field, not just as one form. And so in particular, we can divide this A into two pieces. One that I can call A trivial. This is a connection on a trivial line bundle. And since the bundle is trivial, a connection can be globally defined, so essentially this is a standard one form. But in this path integral, there are also line bundles which are non-trivial, okay, on a general tree manifold. And so there is another piece, we call it A prime, which is a representative of the non-trivial bundle. So for each non-trivial bundle, I pick a representative here, and then all possible connections on that bundle are represented by shifting the trivial one. Because the difference between two connections on a certain bundle is always a globally defined one form. And we should do the path integral on both terms. And so in particular, so as you said, this is a standard one form. But this is quantized in the sense that for each bundle we choose a representative, so this is some sum. Okay? It's a discrete sum. And so in particular, when we do the path integral first on a trivial, for instance, then this is a one form, and so sets dB to 0. There is no field strength for B. B is flat, but one must still worry that there are flat connections which are allowed. But then we have the other, then we have to do this sum here. And then one notices that this integral, so here it is a wedge. Now this can be integrated by parts. And so what this is, well, essentially this is a pairing between, so this object here, now this is the field strength, so this is essentially the first chain class of our bundle. And this one here, well, the pairing is with the Wilson line. So here now there are just flat connections, and flat connections corresponds essentially to the holonomies along the one cycles that we can have in the manifold. So let me call this W of B. And so in particular, this first chain class is an element of H2 of the manifold. Okay, because these are well, essentially two forms. And these Wilson lines are elements of H1. But these Wilson lines, they are holonomies, and so they only, for U1, they only take values on the circle. Okay, because, okay, essentially the holonomy is this object here, and this object here is a phase. So this is in U1. And this object is a natural pairing between these two objects here. And so when we do this sum over all these bundles, essentially what we have here is a sum, so let me simplify here. Let's suppose that there is just one single 2 cycles for these first-chain classes. So it will be a sum of e to the 2 pi I n omega, where this n is this first-chain class, and this omega is this Wilson line, and this gives us the delta on omega, okay? And so this second piece sets to 0 the flat connections, and at the end of the day, this is just equal to a delta on B, up to gauge transformations, of course, okay? Any question? Okay. So yesterday I wrote these dualities between vector models with scalars and fermions. So let me write them again and say a few things more. So I would like to mention some of the checks that has been done. I was a little bit quick yesterday because it was towards the end of the lecture. So one of them was SUN with scalars, equal to UK minus N/2 with fermions. And then the other one was similar, where here there was U and here SU. And we said there are more. So let me mention some of the checks. That one can do, it has been done. So we mentioned yesterday, one can try to look for very small values, okay? We said yesterday, for instance, if we take n equal to k equal to nf equal to 1, this was giving us the bosonization dualities or the fermionization duality that we discussed at length yesterday. In fact, one can even consider the case in which nf is equal to 0, so no matter at all, and then this will reduce to the 11 rank duality of pure Chern-Simons theories that we described, which is actually duality that one can prove, as we said. It's not a conjecture, that can be proved. So this leads to level rank. Then I just briefly mentioned the fact that one can consider the case in which n and k goes to infinity, so very large, with n over k fixed. This is a 't limit. And here also one can do very nice computations of correlation functions, both at leading order and subleading order, although it's more difficult, and they match. One could, I mean, we should try to match the symmetries in these theories. And for instance, in these theories here, where there is SU gauge group and NF scalars, well, there is a global symmetry that rotates the scalars. And well, roughly, the global symmetry here is UNF, okay, rotating these complex scalars. In this theory here, it's similar, so there are NF fermions, so there is a symmetry that rotates these fermions. However, the U1 here is gauged, so the symmetry that acts on these matter fields is only SUNF. But in fact, since there is a Billiam factor here, we discussed that there exists a magnetic global symmetry or topological symmetry whose current is given by essentially the trace of the field strength. And so we have it here. So magnetic. In fact, on both sides, we also have charge conjugation. And, well, U and F is essentially the same as U1 times SU and F. They're not exactly the same, and this is why I'm putting this tilde here, because if one is more careful, one can in fact, and is careful about the global structure of the group, one can figure out that really the global symmetry group is UNF, and it turns out that that's actually UNF mod ZK. And this can be done on both sides. So one can precisely match the global symmetry in these two theories. Let me write it here. Global symmetry. Now, regarding the operators in these theories, well, for instance, in this theory, okay, one can construct sort of mesonic operators when you take some phi bar. These are clearly gauge invariant. But since the gauge group is SU, we can also try to construct some baryons. So we take essentially n of these fields here, and then we contract the gauge index with an epsilon tensor. Okay, this will be, well, if n is large, it will be a large operator, but it's a baryonic operator. And in particular, it's an operator which is charged under the U1 in here. Okay. What is it mapped to in this theory? Well, in this theory, we cannot construct baryons because now the gauge group is U. And so if we take n or k of these fields and we contract with the epsilon tensor, that will be gauge invariant under the SU part, but not under the U part. Okay? So there are no baryons here. So what are these baryons mapped to in this theory? Well, since the baryons were charged under the U1 part here, they should be mapped to operators which are charged under U1 magnetic here. And in fact, they are mapped to monopole operators here. So we can construct monopole operators in the same way as we discussed them in the simple abelian case. And well, it turns out that the bare monopole operators now has a large gauge charge, and so it has to be dressed, and this becomes a large operator. And if one is careful, one can precisely match the quantum numbers between all the different baryons that one can construct here with all the different monopoles that one can construct here. So there is a nice match between baryons and monopole operators. And then another nice check that one can do is try to see what happens if we perform a mass deformations of these theories. Okay, so we can try to give mass to all the fields here and all the fields here. Now, so let me try to see what happens in this first line here. So if we do it in the theory with fermions, well, this is simple, because you said when we give mass to the fermions, essentially we shift the Chern-Simons level, okay, because of this one loop effect. So in the UK side, we turn on a mass for all the fermions. And, well, if this mass is negative, we get some topological theory. Which is this one here. This is some pure Chern-Simons theory. And if the mass is positive as well, we get a topological theory. This time, so with positive mass, we shift this number up. So every time we integrate out some fermion, this shifts by plus or minus a half. Right, as we discussed yesterday. Okay, so what happens in the bosonic theory? Well, here we can give positive mass squared or negative mass squared. because the operator that corresponds to that in this proposal, so let me put a minus there, is this mass term here. So, okay, so if we put a positive square mass, essentially we integrate out these fields and we are left with the pure Chern-Simons theory, which again is a topological field theory. So here we're left with the SUN level K. And so is it the same? So do we get the same phase? Well, yes, because these two topological field theories are the same because of level rank duality, okay? So this nicely matches. What happens with negative square mass? But here is a little bit more interesting because when you give negative square mass, these fields, and we take this mass to be large so that we can do a semi-classical analysis, they will condense, okay? And they will break the gauge group, okay? So here we distinguish a couple of cases. So if the number of fermions is smaller or equal to n minus 2, they partially break the gauge group, and we are left with a topological field theory with smaller gauge group, SUN minus NF at level K. This again is a topological field theory, and once again this nicely matches with the one here, again because of level rank duality. If NF is actually equal to n minus 1, well, in this case the gauge group is completely broken, and so, well, we get trivially gapped state. But in fact, what we get on this side is UK level 1, which you remember is this trivial topological field theory which has just a trivial gapped vacuum. And so also in this case, it nicely matches. If we take NF equal to n, what happens is that all the scalars condense, so they completely break the SU part, but in fact they also break the U1 in the global symmetry now. But now, since they are breaking a global symmetry, there is a Goldstone boson. So this is similar to what we discussed in the abelian case. And so what we get here is an S1 Goldstone. And let's see what happens on this side. Well, now n is equal to NF, so you get UK level 0. And what happens is that the SU part confines and goes away, but the U1, we are left with a U1 level 0, and that is a free photon. So that one is dual to a compact scalar that is the Goldstone boson for the broken magnetic for the spontaneously broken magnetic symmetry. So it matches with this. So all these cases match. However, if we take n and f bigger, can you see here? Maybe not. So, however, if we take, write it here. If we take an f bigger than n, then what happens is that here, okay, again, the gauge is completely broken. Now you further break this global symmetry. You break it even more, so you have more Goldstone bosons. And in fact, they describe some nonlinear sigma model, which is the original from the global symmetry divided by the unbroken global symmetry that you can convince yourself that is given by the following. Okay, so this will be some nonlinear sigma model that describe the Goldstone bosons. And, but we don't see that in the dual, okay? Because here, again, we have some TQFT. So this case seems not to match. And this case is very interesting. I will mention something about this case towards the end. But if we want to stay on the safe side, we can say that, okay, at this point, we only regard these dualities for NF smaller or equal to n. Okay? A more interesting answer will be that, in fact, there is some very interesting physics that probably I will not be able to describe if we push beyond this bound. Okay. Question? Okay. So at least if we stay within the bound, we also have a nice check of phases. And then the last check that, on which I would like to spend some time is related to Toft anomalies, in particular Toft anomaly matching. So this is something that also Ken talked about, so I will partially repeat what he said, maybe under a different, from different angle. And so the point about Toft anomaly is that, well, first of all, we know that quantum field theories in general, well, often have global symmetries, and these global symmetries are extremely important, okay? In the sense the concept of symmetry is extremely important in physics. And for instance, something that we can do when we have a quantum field theory with some global symmetry is to couple this theory to background fields for this symmetry. If we have some symmetry G, we couple to background fields. And this is extremely useful and extremely powerful in general because it gives us observables in the theory. These observables are precisely the partition functions computed on this background. So here we have the action that depends on the various fields in the theory and the background fields. And so how do we couple the theory to background fields? Well, for instance, if this group is connected, we do it in the standard way. So at the linearized level, we introduce the minimal coupling. And then maybe we have to introduce some Siegel terms to try to have gauge invariance, at least at the classical level. Now, when we discuss the symmetry of a theory, it's important or useful to identify what is the faithful symmetry of the theory. And by faithful, I mean that we would like to, so when we say, okay, a theory is a certain symmetry, it means that correlation functions are invariant if we transform all the operators according to G, and so we give a list, if you want, of the group elements in this group. We only want to list the group elements that really do something on the operators in the theory. We don't want to include elements that, in fact, do not act on any operator in the theory, okay? I mean, we could always say that a theory has a very large group of symmetries which do not act on any operator. I mean, this would be foolish. So we want to really list just the faithfully acting symmetry. And so just to give you a concrete example, so suppose that we are studying U1 level 0, so just Young-Mills, a billion Young-Mills with NF scalars. As we said before, so here there is a global symmetry, which is SUNF. This just acts on these complex fields, rotating them in the standard way, and it is SU because the U1 is gauged. But in fact, this doesn't act faithfully. The truly faithfully acting group is SUNF mod ZNF. Okay, why is that? Well, because the center of SUNF is in fact already gauged inside this U1. Okay? Or in other words, if you list the gauge invariant operators in this theory, you don't find the generic representations of SU and F. You only find representations that are invariant under the center. Once again, because the center really is gauge, and so if a representation, if some operator was not invariant on the center, it will mean it is not gauge invariant, okay? So why it is useful to identify what is the faithfully acting symmetry? Because suppose, like in this example, that our faithful symmetry, in fact, is some naive symmetry. In fact, as in this example, modded out by some discrete group. Okay? Now we want to construct observables in the theory by coupling to background fields. And now the crucial point here is that the bundles for this group, for this quotient group, are more general than the bundle for this group here. So there are more bundles for the faithful group than bundles for the naive group. And so if we are naive and we say, okay, the symmetry is only this one, then we will be missing a lot of interesting observables in the theory, because we would limit ourselves to bundles for these groups, which are less general than bundles for this group. Okay? Of course, that would maybe not be a big mistake, but we would be missing some interesting physical information, some interesting observables. And just to give you an example of these facts of the bundle, so for instance, suppose that you're studying S2 times S1, then there are no non-trivial, topologically non-trivial SU2 bundles. But if you look at SO3 bundles, there are non-trivial. In fact, these non-trivial bundles corresponds to the monopoles of SO3. Another example might be if you go in 4 dimensions and you study instantons. So for instance, you take some SUN theory and you look at instantons. And well, you know the instanton number. This was also used by Ken. Now this instanton number is integer, okay? There is an integer number of instantons, but if you study a theory in which the gauge is SUN mod Zn, which is also called PSUN, then there are more general bundles, so there are more general instantons for which this quantity is fractional. So, well, if you want, of course, the number of instantons is still integer, but if you use the same normalization that you had before, you get fractional instanton number, okay? So there are more bundles. Okay. So we have in general, we have a theory. We try to identify the faithfully acting group. And then we couple the theory to gauge fields for this group, and we try to construct observables. Now, what might happen is that the theory has Toft anomalies. So what does it mean? Well, if you look at infinitesimal transformations for G, so suppose that this G is continuous and we just look at transformations which are close to the identity, one way to phrase Toft anomalies is that if you look at correlation functions at separated points, those are invariant. Okay, it's very important to restrict to separated points, so we look at some correlator of some operator. Okay, and these points are not the same. Oh, but the statement of the symmetry is that this symmetry group G will act on the operator. The operators form representations of this group. And if we transform all the operators in a correlation function, this correlation function is invariant, okay? As we are this is the statement that really this is a symmetry. G is a symmetry. However, what might happen is that if you look at the contact terms, when some of the points collide, the contact terms are not invariant under the symmetry. And in fact, there is no way to make these contact terms invariant under the symmetries. So at separated points, they are invariant. But contact terms cannot. And when I say cannot be, I mean that one always has the freedom to act local counterterms to the theory to try to cure this problem, but the statement of the anomaly is that there is no way to do that. Now let me stress once again, a Toft anomaly doesn't mean that the symmetry of the theory is spoiled. The theory does have the symmetry because correlation factors at separated points are invariant under the symmetry, but there is a feature, I mean we should call it a feature in the sense that it is an observable of the theory, a characteristic of the theory that shows up, for instance, in this formulation in the contact terms. So it's different, as also Ken stressed, it's definitely different from gauge anomalies, which make the theory inconsistent, and it's also different from the ABJ anomaly, which tells us that what we thought that was a symmetry at the classical level is not a symmetry in the quantum theory. For Toft anomalies, they do not spoil the symmetries. Now, another way to rephrase this in our language of coupling to a background field is that you compute, so you couple to some background gauge field, and you compute your partition function. You would expect this partition function to be invariant under gauge transformations under B, but in fact is not. So, so somehow this is really a function of the connection, is not just a function of the bundle. Okay, so let me do the infinitesimal case. Okay, so these are an equivalent way to phrase this statement here. Actually, if you use this coupling to bundles, the statement is a bit more general because in fact, we don't have to limit ourselves to small gauge transformations, but more generally it can happen that this partition function is not a well-defined function of the bundles. Or if you want, it cannot be consistently defined as a function of bundles. Okay, and I will explain this point in 10 minutes or so. Okay, so what do we do in this case? So we have this partition function cannot be consistently defined as a function of bundles, but we would like to do that because we want to construct observables. So what do we do? Yes. Because so in a theory, if you want, the objects that you can try to, I mean, the first object that you try to observe in a laboratory corresponds to a correlation function at separated points. So you have some material and you do some perturbation at one point and you measure what happens at some other point. And these are invariant under the symmetry. So if you want, this is the statement that the correlation functions satisfy word identities. If the symmetry are continuous, the currents are conserved. Okay? How would and I will review this in a second, how would the anomaly show up? Well, it will show up as the fact that the currents are not conserved when we put the theory on a background. But if you want, this is a strong operation that we do on a theory. For instance, we think of the standard model with its global symmetries, we cannot really turn on a background for the global symmetries. I'm sorry? No, so here I'm not using any Lagrange, I mean, this is beyond any Lagrangian description. If the theory has the symmetry, it means that you can always define gauge invariant operators, all the operators in the theory, they fall in representations of the symmetry group, and when you compute correlation functions at separated points, even of the composite operators, if you want composite operators okay, it's not just a Lagrangian concept, but I mean, all the operators in the theory, when you compute correlation functions at separated points, those will be invariant under G. In fact, most quantum field theories that we study, they do have Toft anomalies. I mean, most symmetries that we use in quantum field theory, they have Toft anomalies. In fact, if you want, well, the ones that we can gauge, they will not have Toft anomalies. Because, of course, if we gauge a symmetry with a Toft anomaly, that anomaly becomes a gauge anomaly. And then would make the theory inconsistent. So the symmetries that can be gauged, they do not have Toft anomalies, but in general, symmetries, they do. Any other question? Okay, so what do? We really want to construct these objects. And what can we do? This is not necessarily the only option, but what can we do is similar to what we did with the Chern-Simons theory. So we can take our manifold MD and we attach to it some other manifold in dimension D plus 1. So somehow we extend the manifold spacetime in the bulk. And we couple our theory to some classical theory that lives in one dimension more. In such a way that the whole system now is consistent. And the whole partition function on this extended manifold can be consistently defined as a function of bundles. And this is called anomaly inflow. Now, again, we should ask, okay, is there a dependence on the extension? This is what we did with Chern-Simons theory. Now, if we discover that, in fact, we extend, but there is no dependence on the extension, this means that, in fact, the D-dimensional system was consistent per itself. This is, in fact, the way that we use to construct Chern-Simons interactions, or the Chern-Simons functional. We need to extend, but at the end, there is no dependence on the extension. So in that case, it will mean that, in fact, there is no anomaly. And in fact, instead, when there is an anomaly, what happens is that we need to extend, but in fact, there is a dependence on the extension. So somehow, the background fields, in order to define consistency of a partition function, we need extra data. We need to specify some extension. And then we can ask, okay, what is the dependence as we change the extension? And once again, the trick is that if we want to compare two extensions, we close the manifold. And so we evaluate this classical theory on closed manifolds. So let me call them y d plus 1. And so essentially, these classical theories on closed manifolds, they are the way that we can use to quantify the Toft anomaly. So here, if we look at what classical theory we have here, this gives us a way to quantify the anomaly. In the sense that we do not just say, okay, the theory has an anomaly, but we can say how much, if you want, okay? We classify it by these classical theories. Okay, and then something very nice about this anomaly is the fact that this theory that we put here in the bulk is a classical theory. While, of course, the one on the boundary was a dynamical theory with a path integral and so on. And so what happens is that if there is some RG flow in this theory, Well, essentially, this RG flow doesn't do anything in the bulk because this is just a classical theory, just some integral of some local integral or local functional of background fields. And so this object will be exactly the same in the UV and in infrared. And so in this sense, these objects are G invariant. And so if we have some theory that is UV free, we define it in terms of some Willicke couple Lagrangian, usually we can compute this anomaly, and then we know that it has to be the same in the infrared. So these anomalies can be exactly computed at strong coupling, okay? This is why they are so powerful. And if you want the Toft anomaly matching, it's just the statement that if you propose some infrared effective description for some theory, it has to reproduce the same Toft anomaly, okay? So let me give you, let me just quickly review what happens in the familiar case of the Carroll anomaly, just because this discussion might be quite abstract. So suppose we just take a free fermion in 4 dimensions. Okay, there is a symmetry that rotates this fermion. And since there is a symmetry, there is a current. Current is conserved. The symmetry is really there, no doubt about that. This current is conserved. This operator is conserved. However, we can try to couple this theory to some background field because we have this U1 symmetry, so we couple to a background field, B mu, and we compute the generating function. Well, this partition function is the generating function of current correlators. And now we have here our background field in the covariant derivative. And now we can ask, okay, how does this partition function change if we perform a gauge transformation? Okay, this is abelian, so simple. And how does it change? Well, if we perform the variation of the partition function, what do we have? Well, we have the variation with respect to the argument times the variation of B, which is just the gauge transformation. And then we just notice that this is the generating function of correlators of the current. So this is essentially IZ times the 1-point function of this current, but now will be the 1-point function in the presence of a background. And then we just integrate by parts. And we get the standard result. Which is expressed in terms of this conservation of the current now in the background field. And here it comes the computation of the Carroll anomaly that I'm not going to repeat. But as you know, in the Carroll anomaly is the statement that in the presence of a background, now this current is no longer conserved. The divergence is proportional to the background. So in particular, d mu, j mu is equal to, well, essentially f wedge f. And here there is some coefficient, some number that this is the anomaly, a number that quantifies the anomaly. And so well, if we take that and plug it in here, we get some infinitesimal variation of this partition function that, if we want, we can integrate and write the finite variation. which is this. So when we perform a gauge transformation, the partition function is not invariant. It picks up a phase, but this phase is just a C number. So this F is only depends on the background. Okay, it's not an operator, it's just a C number. So even though, okay, it's not a good function of bundles, still we know very well how it transforms. And in fact, we could cure this problem by coupling the theory to a bulk. And what do we have to write in the bulk? Well, we write a 5-dimensional Chern-Simons term. Okay, because if you do the gauge transformation of the Chern-Simons term, now the manifold has a boundary, and so you immediately see these two are gauge invariant, but here you pick a lambda. Okay, these F wedge F. So we pick up a lambda, which is precisely what we have here. And so the combined system, whose partition function is the product of the two partition functions, is invariant. Okay, and so the partition function of the combined system is in fact a well-defined function of the bundle. Okay? Any question? Yes?
Now, what happens now if you try to do this gluing?
Say again?
If you try to do this gluing of
Yes.
parts, problem if the Chern-Simons has the integer partition.
Yes, exactly, but this classical theory, so the point, so when we constructed, if you want, is, so now Chern-Simons, so before Chern-Simons was living here on the boundary, now Chern-Simons is living in the extension. Now, when discussing Chern-Simons on the boundary, we wanted, so we said, okay, in the extension, you need to put F wedge F. And F wedge F has the property that when you, well, it was suitably normalized, has the property that when you integrate it on a closed manifold, you get something which is a multiple of 2 pi. And so if we look at this integral mod 2 pi, this is 0. So we find something that mod 2 pi evaluates to 0 on closed manifolds. And so we say, okay, then Chern-Simons is really a 3-dimensional object, even though we might need an extension to define it. But here is different, because now what you see in the extension, we put this Chern-Simons action. So now what we have here, now the extension is our Y5, and we have the Chern-Simons action evaluated on this. And this is not an integer. In fact, it's a generic real number. And so you see that really there is a dependence on the extension, and in fact, this represents the anomaly. And in fact, this number here is the Carroll anomaly. So it's a change of perspective where we put Chern-Simons theory this time. Any other question? Okay. So this is just a case, I mean, the Carroll anomaly you know, is just presented maybe from a different angle. But now we go to 3 dimensions, and the thing in 3 dimensions is that in odd dimensions, in general, there are no Carroll anomalies. So there is no anomalous non-conservation of the currents. In odd dimension, the currents that are classically conserved are still conserving the quantum theory. So does it mean that we don't have anomalies? No, it's not true, because we can still have anomalies that are sensitive not just to the structure of the group close to the identity when you do small variation, but they are sensible to the global structure of the group. So we can call these global anomalies. Global Toft anomalies. And so at this point, so I would like to jump to an example since I don't have much time, but essentially what we have to do is just to apply this very same philosophy and see what happens. So let's consider the following theory, SU2 level K with NF scalars. And then let's see. So what is the global symmetry in this theory? Well, this is a bit special because SU2 is the same as USP2. And so really SU2 has only pseudo-real representations. And so it turns out that the global symmetry in this theory is USP2NF. But in fact, again, we have to divide by the center because the center is gauged here. So it's very similar to the case that I discussed before. So this is the global symmetry, the faithful global symmetry. And now we want to turn on backgrounds for this symmetry. So how do we do that? Well, if you look at these scalars, so these scalars are coupled both to the gauge fields and to the background fields. So in particular, these scalars are coupled to the following group, or to the following bundles, SU2 times USP2NF mod Z2. And here I divide by Z2 because this Z2 is the common center, but they do the same thing. So the center of this puts a minus for all the fields, but also the center of SU2 gives a minus to all the fields, so they do the same. I don't want to double count. Okay? So the scalar fields are coupled to gauge fields for this group. Now SU2, it has a Chern-Simons level, Chern-Simons term at level K. What about this global group? Well, here too we can turn on some level. This will be a Chern-Simons term for background fields, but this is essentially a local counter term. So we could set it to 0, but we could set it to some other value. In fact, when we try to remove the anomaly, we should try with all possible counter terms. If there is some counter term that allows us to remove the anomaly, that is not an anomaly, okay? So that L might be 0 or might be different from 0. And now the point is that Chern-Simons terms, we have repeated this many times, are not defined for generic values of the coupling. They're only well defined if the coupling satisfies some quantization condition. So what are these quantization conditions? Well, first of all, K should be an integer. L, in the same way, should be an integer. But now we also have this quotient here. And the quotient gives us more constraints. Essentially because one way to understand this quantization, remember we do some large gauge transformation, and we want that the Chern-Simons functional jumps by a multiple of 2 pi. But if we quotient the group, then there are more general gauge transformations for which the winding number is fractional in a similar way as the instanton number could be fractional. And so since now we have, you get a more stringent condition in this group, it turns out that there is another constraint that K and L have to satisfy if you want that term to be gauge invariant. And this condition is the following. Okay, so these are the conditions, if on the quantization condition on these counter terms, on these Chern-Simons terms, such that the functional is, the three-dimensional action is well defined. And now you see, if you take K odd and F even, okay, these are parameters which are fixed in our theory. We can play with L because it's a local counter term, but we cannot play with these two. So in this case, you see there is no way to solve this equation. Okay, so what does it mean is that there is a Toft anomaly. So this action cannot be well defined purely in 3 dimensions. Is this point clear? At least the idea? And, okay, so what do we do? Well, since this Chern-Simons functional is not well defined in 3 dimensions, we need to extend to 4. So for instance, let's set L to 0. We only have the Chern-Simons term for SU2. So we have our K over 4 pi integral. And now we extend, so we go to some Y4, or maybe I call it X4, the one with boundary, trace of F wedge F. And here the point is that, of course, this is well, we extend it, so now this is well defined, okay, because this is gauge invariant by construction. And now we want to quantify the anomaly. So to quantify the anomaly, we ask, okay, what is the evaluation of this object on closed for manifolds? And as we said before, if this f is in SU2, then this is an integer, well, it's a multiple of 2 pi, so we can say that this is 0 mod 2 pi. Right? This is the Chern-Simons function for SU2. But the point is now we are turning on more general bundles, because now we have bundles in this object here, and when the bundles are in that object here, this is no longer an integer. It is no longer 0 mod 2 pi. But in fact, it turns out that it can be rewritten in terms of quantities that only depends on the background. Now, I'm going to write the expression. It will not be, it's a bit technical, so it's not important, the particular expression. I just write it for completeness. So this is essentially the second Stiefel-Whitney class of the bundle. The important thing is that so the value of this functional on closed manifolds can be written entirely in terms of some characteristic class, some object that only depends on the background fields. And this is good, because if we found that actually what we have to extend in the bulk are the dynamical fields, this will be very bad. I mean, we want our dynamical theory to still be three-dimensional. If you want, that would be some gauge anomaly. Okay, even the dynamical theory is not well defined in 3 dimensions. This should not be true. We know that the theory makes sense. And in fact, it turns out that the full dependence can be completely written in terms of some object, maybe some complicated object, it doesn't matter, which is only a function of the background fields. And so we can regard this classical theory, this is just some integral, essentially some characteristic class of the flavor bundle, as a quantification of the Toft anomaly for these theories. Okay? Is the idea clear? Okay. And in fact, it turns out that one can generalize a little bit this example. For instance, taking USP to n. There is a similar, here we get an n. But now, for instance, these theories are involved in one of the dualities. So I've discussed the case in which you have SU, U. There is another version in which you have USP, USP. And so you can take the 2 theories, you can do this computation that we did, and you can check that the Toft anomaly appears equally on the 2 sides. So when one side is a Toft anomaly, there is the same anomaly on the other side. And when it's 0 on one side, it's 0 on the other side. And so this can be used, for instance, to do this Toft anomaly matching in this particular case of the dualities. Okay? Similar thing can be done for the SUU. I didn't present that because the computation is more involved and more complicated. Okay. Yes, I think I will stop here.